Hello SGD, Sacred Geometry Decoded. This will be part 16 in the series, looking at understanding the sciences of the Great Pyramid, the pyramids in general, and how it leads to a series of ancient geometric, astronomical, mathematical, musical sciences which still define the science and much of the world that we live in now. Without weights and measures, there is no science. So whether it's Nu-Afuzi in the Far East, Hermes, Mercury, gods of weights, measures, geometry, measurement, Thoth and Sheshet, ancient Egyptian gods of knowledge, math, architecture, record keeping, alchemy, chemistry and medicine, and weights and measures. What they share is a geometric, metrological or measurement, and linked to the sciences and the crafts or the arts such as architecture. So previous episode to this one, and I'll be exploring this a lot more, the connection between the meter, the Egyptian raw cubit and the foot, for instance, which I've been repeating throughout the series, and the geometry. So the idealized measures of the Great Pyramid. In the previous one I went through the fact that each side of a pyramid has a slight variation, but as a nice rounded off essence, you could say that each side of a pyramid is 440 Egyptian raw cubits wide at the base and 280 Egyptian raw cubits high, which gives us a very, very good close approximation of pi as well as phi, and some other lovely geometry connected therein. And this is a proportion, so it doesn't matter whether it was Egyptian raw cubits, jelly beans, mobile phones, however you choose to measure it, the proportions are inherent. But the measurement itself, this is what's important, that it also contains connected information. Now, for instance, one Egyptian raw cubit is pi over 6 meters. Very, very important, because this will link to the link between such as seed of life geometry, linking to 1 meter diameter gives us an Egyptian raw cubit. Now, if you had 1 meter radius, you have a pendulum of 1 second, as in 86,400 seconds per day. Multiply that by the maximum visible base of a pyramid, you get the equatorial circumference of the Earth. Multiply that by 86,400 seconds per day, you get the polar diameter of the Earth. Therefore, the maximum visible base, two sides of the pyramid, including the sockets, is the rotational speed of the Earth per second. Now this has the meter, the foot, the cubit are linked in this geometric, mathematical, astronomical way, which is just phenomenal, exquisite, beautiful. So we can close these down. Now this is the idealized pyramid. So the half base of 1 would be 1.27272727. That's the idealized number, 1.272727. Now, but the actual reality of a pyramid is that each side has a slight variance. And so the longest side, the southern side, is 756 feet and 1 inch essentially. The northern side is the shorter side, and that is 20 centimeters shorter. And these elements come together. So now there in red, I have now slightly, I've exaggerated it, but what we have is on the corner of each pyramid we have the sockets. But what's important for this particular episode is the socle, or the paving stones on which the pyramids sit. They're another engineering marvel. The precision they vary by only an inch. The pyramid is not perfectly level. It varies by an inch, and just like the slight imperfection on each side of a pyramid, this 1 inch variance between the socle from the highest to the lowest point actually contains beautiful information. But as a nice rounded off number, just to explain briefly, the socle is 55 centimeters high, and there you get an idea of this gentleman sitting on the socle. So you can see basically from your knee to the soles of your feet. So it is 55 centimeters. Now this is an important feature because this has to do with geometry, architecture, and weights and measure. So the proportions of the pyramid, doesn't matter how you measure it, what unit, the proportions stay the same. But this proportion of the Egyptian raw cubit of pi over 6 meters. Now I've rounded it off ever so slightly. That's 52.36 centimeters or 523.6 millimeters. Pi over 6 is 523.599 millimeters. So I've rounded it off by 0.001 of a millimeter. That's 1/40th of the thinnest human hair. So rounding it off to 0.5236 meters is infinitesimally small to change. But there is another level of geometry embedded in the proportions, which link to the measurement of the pyramid. Okay, now I have to pause a moment. Okay, so the pyramid, phi and pi, and so at 7 to 11, if the half base is 1, then the height would be 1.272727. That's the idealized measure. Now, 4 problems of antiquity, and one of those is circling a square. Now, we mentioned this in regards to astronomy, but essentially the pyramid is an excellent, very, very close approximate of squaring a circle. Now, technically, it cannot be done with compass and square edge, but squares and circles. So with the Great Pyramid is 7 to 11 proportions, which is repeated in the Meidum Pyramid, or the capstone at the Red Pyramid, which just happens to be 1 meter high. We have squaring a circle, squares and circles. So where's the link to that? So squares and circles, this is what the geometry embedded in the pyramid. So each side of a pyramid, through my own investigation and looking at the actual surveys and including the slight variances on each side, these very close approximates of phi and pi actually reach a precision, essentially perfection. Fractions of a millimeter, actually like 1/1000th of a millimeter difference. But so each side of a pyramid, including the slight variations, not only makes perfection, but actually leads to that each corner, each side of a pyramid has a very consistent meaning to it. And what I mean that is geometric. One corner is ratio, one corner is meter, one corner is astronomy, and one corner is geometry. And that's the corner we'll be looking at now, and that's the northwestern corner. So we go around, and the northwestern corner. Now just a reminder, we have the actual measures of the pyramid. So there is no one side of a pyramid is exactly the same. Now what we do have is a great approximate of phi and pi, but there's deeper levels of information. The important part is 1 Egyptian royal cubit at pi over 6 meters. Now also a reminder, we need to include the socle, the paving stones. This gives an added dimension to the size of a pyramid. It adds height to the pyramid. So northeast corner, now we already mentioned squaring the circle. So squares and circles, yep. Now what happens if we use the actual measurements of the pyramid is at the northeast corner. If you take a 2-dimensional view of the pyramid, if you basically cut it in half, what we do is we have the height and the northwestern half base. So from the very center of a pyramid to the edge, 146.63928 meters, and from the center to the base, 115.1820. Okay, now what happens is if we divide the height by the half base, instead of getting 1.272727, we get 1.273236. Why is that important? Well, because in 2 dimensions, now we squared a circle. Now what happens if we inscribe a circle inside a square? What happens is that the ratio of area, the area of a circle compared to the area of a square. If the area of a circle is 1, the area of the square is 1.273235, etc. That's 2D. That's 4 over pi. So the good approximate of 4 over pi, as we can see here at 440 wide by 280 high, very good, very, very good approximate, essentially reaches perfection to the fifth decimal place, well above any acceptable. How do you measure to that precision? Well, we're talking with a millimeter either way would change this. So what we have is the area of a circle inside a square at 4 over pi. The northeast corner, viewed as a 2D object, so we've sliced the pyramid in half, we have 4 over pi, the area of a circle inside of a square. But there's more. Now the pyramid is three-dimensional, so instead of cutting it in half and thinking of it 2D, let's look at the corner of it and think of the pyramid as it is a 3D object. So 2D gives us a two-dimensional area of a square around a circle, or a circle inscribed inside a square. Well, what happens if now we add a dimension to the pyramid? We add the socle, the paving stones. We add this height to the pyramid. So from the peak to the corner, including the socle, is 220.0559, etc. meters. That's including the socle. And we have the half base from the corner to the midpoint, 115.127, and divide 115.12727 by 220.0559, and we get 0.52355 as a proportion. Pi over 6. Pi over 6 meters equals 1 Egyptian royal cubit. Previous episode I went into the actual average of all four sides of a pyramid is 0.52355. Well, 0.2355, it's the same. And again, within a tenth, a hundredth, a thousandth, one hundredth of a thousand. 100,000. Yeah, that's the purport. Now, why is that relevant? Firstly, because the Egyptian royal cubit is pi over 6 meters. That's a measurement. Well, the area of a sphere, okay, sorry, typo there, it's not a sphere, it's a sphere. A sphere inside a cube. So we've inscribed a circle in a square, which is 4 over pi ratio of area. That's two-dimensional. The Egyptian royal cubit itself is a one-dimensional measurement, but we also have 3 dimensions because a sphere, again, pardon the typo, a sphere inside a cube has a ratio of volume of pi over 6, or 0.5235987, which of course is the... Now I just rounded that off, but again, that is the number, because that you divide a meter, you're talking tens of thousands of a millimeter. It's yep. And so if you include the slight variations on each side of a pyramid, the northwest corner encodes the two-dimensional area of a circle inside of a square, 2 dimensions, area, and the 3-dimensional volume of a sphere inside of a cube. We've already squared the circle. We have the one-dimensional unit of measure itself, the Egyptian royal cubit in meters, being, for all intents and purposes, exactly the same number as a sphere inside a cube. And it just so happens that the angle in tan, in trigonometry, so the base angle, is also 4 over pi. And we have in trigonometry the angle in cosine will also bring us to the golden number. This is an extraordinary set of perfectly measured, beautiful coincidence Measure, measure, the truth shall set you free.